Welcome back, class. In today's video, I want to talk about a couple concepts. First one being solution equilibrium, and the next one being the effect of temperature and pressure on solubility. So, solution equilibrium. So this kind of is a similar idea to what we talked about previously in chapter 12, I believe it was, when we talked about the equilibrium that forms between a gas and a liquid in a closed container, right? The vapor pressure, right? You get evaporation, and then you start to get condensation, and then eventually you get to a point where the rate of evaporation is equal to the rate of condensation, right? We reach what we call the dynamic equilibrium. Well, something similar happens when you form a solution. So, for example, when I dissolve sodium chloride, initially, right, we get a lot of what we call dissolution, right, or dissolving. So we get the ions breaking apart, right, because of the energetics that we've talked about. But as the solution becomes more concentrated, so in other words, the concentration of sodium ions and chloride ions, or dissolved sodium chloride, right, builds up, right, then we start to see some what we call recrystallization, or going from the dissolved form, the ions, right, back to the solid crystalline form. The ions recombine, in other words. At some point, these two processes, dissolution and recrystallization, become again balanced, right? The rate of dissolution equals the rate of recrystallization. We reach a point of dynamic equilibrium. And at this point, the amount of material, in this case sodium chloride, in solution doesn't change, right? So it's that back and forth. So the amount of dissolved sodium chloride stays constant, because every time a new ions dissolve, ones are recrystallized to take its place. So at this point, right, the important thing to note here is that at this point, the concentration of sodium chloride does not change. Now, another way to say that is just the amount of sodium chloride that has dissolved doesn't change. So this brings us to this idea of how much we can dissolve, right? So at this point, we've reached that solubility limit that we talked about. So when we reach that dynamic equilibrium, we've dissolved as much as we can in that particular amount of solvent under those conditions. And we've created what we call a saturated solution, right? So if I add any more, in this case sodium chloride, it won't dissolve. It'll just sit there and not dissolve unless I change something else, right? I add more water, or I change the temperature, which we'll talk about in a minute. Now, up until that point, if you're anywhere below this limit, right, you are what we call unsaturated, right? You haven't put enough sodium chloride in there to reach that dynamic equilibrium, so everything has dissolved, right? Now, a situation where you have more dissolved than what should be able to dissolve under a given set of conditions, that situation is referred to supersaturated, and we'll talk about a scenario where that might be able to occur a little bit later. So this doesn't always occur, and it doesn't occur just under normal conditions, right? We have to do the things a little special to make it happen. And these kinds of solutions are often unstable, meaning a bunch of material, a bunch of the solute will come out of solution or precipitate under, disturbances if it's mixed or these kinds of things. But some can be actually quite stable if they're left relatively undisturbed. So let's use this idea to think about the effect of temperature. So first thing we're going to look at is the effect of temperature on the solubility of solids. So if you look at the graph here, what we have is solubility curves. So what these lines represent is the solubility limit, right? The saturation point. So from a data standpoint, or from a graphical analysis, right? If you are anywhere on the line, right? So here's the sodium chloride line. So at 25 degrees, let's say, right? The sodium chloride crosses right there. Remember, that was 36 grams, right? So if I'm right on that line, I have the saturated solution. So the lines here represent the saturated solution under the given temperature. If I am below the line, that's unsaturated. If I'm above the line, that would be supersaturated. And so these can be used a couple ways, right? We can look at a given temperature and we can check out what the solubility limit would be. That's one way to use these. The other thing that they allow us to sort of visually see is that for almost all materials, and again, these are ionic compounds, so for almost all ionic compounds, the solubility goes up with temperature. So as we go to higher and higher temperature, we see an increase in solubility. Sometimes that's a very dramatic, rapid increase. Other times it's a more subtle increase with sodium chloride. And of course, there are always exceptions to the rule where you actually see a decrease. Now, these are, again, the outliers, not something that we're really going to focus on. So what we want to remember is the solubility of almost all solids increases with increasing temperature. So this is how we can do things like purification by recrystallization, right? So we can, dissolve something, heat it up, dissolve it at a certain temperature. We can cool it down, lower the solubility, and oftentimes what that will then occur is that we'll get that solute to come out of solution, to precipitate or crystallize out of solution at the lower temperature because the solubility is now lower. And when that typically happens, we get quite pure material crystallizing out. So this idea of recrystallization, or taking advantage of the effects of temperature on solubility, is one way that we purify materials. So the effect of temperature on solids. Now let's look at gases. So how does temperature affect the solubility of gases in a liquid? Now again, of course, we're going to focus on water, and we're going to use probably the most common example of a gaseous solution, and that is carbonation. So carbonation, remember, is carbon dioxide dissolved in water. And if we look at our two pictures here, what we see is that if I take a bottle or can of soda, right, that is cold, right, and I pour it, I get a little bit of bubbling, but not a whole lot of bubbling. Right? So what that's telling me is that the carbon dioxide is staying dissolved. Right? If I take warm soda or warm carbonated beverage and I pour it, I get much more foaming. In other words, more release of carbon dioxide. So the conclusion that I draw from this is that the carbon dioxide is less soluble at the higher temp. And that's exactly what we see, right? Is that the opposite of what we see with solids. As we go up in temperature, the solubility of gases actually becomes lower. And this goes back to the idea that those gases, which are almost exclusively nonpolar, right, like carbon dioxide, do not make very strong interactions or intermolecular forces with the water. And so when they get more energetic, higher temperature, they get more thermal energy, it becomes much easier for them to escape the solution and therefore bubble out. If you keep it cold, those gases don't have as much thermal energy. It's harder for them to escape, so they remain in solution. So gases exhibit the opposite behavior of what we see in solids. So while solids more soluble at higher temperature, gases less soluble at higher temperature. Now, what about pressure? Now, let's look at the second picture here. So here is our typical carbonated beverage in a sealed container. In this case, a can. It could just as easily be a bottle. Now, when you package a carbonated beverage, it's packaged under high pressure. This is why we can't squeeze the can, right? So there's always a little bit of airspace in there where it's filled with a high pressure of carbon dioxide, typically something like 3 to 4 atmospheres. So 3 to 4 times the pressure of the outside air, right? So this is again why you can't squeeze it. As soon as you open it though, all of the CO2 here is released, right, in this airspace. That means now the pressure on top of this liquid is much lower. It's atmospheric pressure, right? 1 atmosphere. What this means is that the carbon dioxide that you've essentially forced into solution here is going to start to bubble out. And so the idea is when we package carbonated beverages, we force carbon dioxide to dissolve by putting high pressure of that gas on top of it. So basically the carbon dioxide here acts like a big hand, sort of holding all of that extra carbon dioxide into solution. And then when we remove that hand, open the can, a lot of that carbon dioxide starts to bubble out. Now, it doesn't, of course, come out all at once, and that's why we get the initial sort of big release, the fizz, and then we get the slow bubbling out, right? This is, the continual sort of fizziness of a carbonated beverage as that CO2 slowly bubbles out of solution until it reaches what would be the normal solubility under those conditions, right? Which is what happens when it goes flat, right? When it loses that fizz. So we can look at it here a little bit more, right? We have a setup here where we have a dynamic equilibrium setup, right? Where we have a certain amount of gas in solution, right? And so gas is coming out of solution, going back in at a constant rate. So this is what happens when we have something sitting out in the open, right? There's always a small amount of gas dissolved in those liquids, right? Whether it be, nitrogen and oxygen from the air, or if you put it in some sort of artificial environment, whatever that gas is, right? There's always gas dissolved in those liquids. Now, you know this and you've seen this, right? Just think about heating water and you see when the bubbling that occurs, not the boiling, but when you first start to heat it up, you get tiny bubbles that will form on the bottom typically and start to bubble out. That's the gases coming out of solution as you raise the temperature. Now, but what if you increase the pressure? So you take some sort of piston here and you lower it down. This would be the same thing as pumping in more gas, right? When we pressurize a carbonated beverage container, so we make the pressure now higher here, right? We take the same amount of gas, much smaller volume, higher pressure. So what that's going to do is it's going to force more carbon dioxide into solution. We create a higher concentration of carbon dioxide. And eventually we get a new equilibrium, right? This would be the equilibrium, say, inside a can. Now, opening that can disrupts the equilibrium, right? That's like taking this piston and just pulling it away. And at that point, the arrow of stuff coming out of solution becomes much bigger, right? In other words, these two things, the arrows here trade places, and all of that gas starts to bubble out. after you've opened the can. Okay. So this is the idea. Now, we're going to do our first example looking at quantitative here. This effect of pressure is something that we can quite easily quantify. Remember, gases are nice and easy to study usually. And there's a nice simple equation called Henry's law that relates how soluble the gas is to the external pressure of that gas. There's a direct relation there, as you might expect. Right? The higher this pressure is, the higher the solubility is. Now, of course, there is a constant that relates these two, right? And this is called the Henry's law constant, and you can see it here for several gases. Now, this is something, of course, that would be given to you. You don't have to remember them. But if you notice, the vast majority of these are small numbers, right? Gases are not terribly soluble in water, right? Polar versus nonpolar. And this is called the Henry's law constant. Now, I will point out one peculiar example here, and that is ammonia has a Henry's law constant that is actually larger than 1. It's 58. Now, you can probably guess why this is, but if you can't, remember what I just talked about, right? What's going to cause these not to be very soluble, right? The fact that these are non-polar, right? They cannot develop strong intermolecular forces with the water, so there's nothing holding them in solution very strongly. Ammonia, right, is the one example here that is polar, right? So ammonia can actually develop hydrogen bonds, right, with water, right? And so it can make a much stronger interaction with the water. Therefore, it's harder to, more resistant to coming out of solution. It's going to stay in solution. It's going to have a higher solubility, and therefore a higher Henry's law constant here. Okay, so we're going to just close this section by doing an example problem here. So let's take this problem here. What is the solubility of carbon dioxide in water at 25 degrees under a pressure of 2.6 atmospheres of carbon dioxide? So this would be the scenario where, let's say I package a carbonated beverage and I package it under 2.6 atmospheres of carbon dioxide pressure. How soluble will the CO2 be, or how much CO2 will I put into solution? Now, from the table, right, the Henry's law constant for CO2 is 3.4 times 10 to the negative second. Notice the units, molarity. So remember our concentration unit of molarity that we learned about? Per atmosphere. So solubility per atmosphere of pressure is the basic idea. Okay, so let's think about our equation. Right? The solubility of the gas is equal to the Henry's law constant times the pressure of the gas. So for this example, right, our Henry's law constant is 3.4 times 10 to the minus 2 molarity per atmosphere. Our pressure, given in the problem, 2.6 atmospheres of carbon dioxide. So if we go through our problem, notice our atmospheres cancel out as units. We go through and do the math, and we get a solubility, in this case of CO2, that's equal to 0.088 molar. So under these conditions, you're going to dissolve 0.088 moles of carbon dioxide per liter of our solution. Right? Now, we might say this is a really small number. Yeah, it is, but think about what the normal solubility is, right? It's going to be, quoted by the Henry's law constant, right? Normally, this would be 0.034, right? Molarity per 1 atmosphere. But now you're at 2.6, so it's going to be 2.6 times this. So while the solubilities aren't great, as you increase the pressure, you force more into solution. So really simple problem, really nice easy equation where we can see how the solubility of gases will increase as you increase the pressure. All right, so that's all for this time. Next time, we will dive much deeper into this concept of concentration. So here we discussed molarity. Now, molarity is the one that we know, but there are many ways to express the concentration or the amount of solute in a solution, and we're going to explore those in the next video.